can I just show of hands, how many people are in the afternoon section? Okay. So I'm going to go through this super quickly because we went through it in detail in the morning. The scripts, so everybody knows too. Here. So what I'm going to show you now, the functionality and the code that I walked through is downloadable. There's two examples. The basic premise of this is that if you have an object, say this is the cube in top view, that this box or this cube we want to increase in scale or reduce in scale based on the proximity of this object to the user. So if you look at the Unity file, as I get close, it's omnidirectional because it's vector-based, three-dimensional vector-based. But if I get a certain distance away from this, we want this to shrink down. Okay? And then as I move away from it, it expands back out. So it's a really simple process of just trying to calculate from the object, from every object, to the player, how far is that vector? That's the first part of it. There's a parameter here. Let's just look at the script. Okay, so I've got a few parameters. I've got the object I want to track. I've got some flags. We'll talk about that in a second. And I have this area of effect. This area of effect is being used so that this condition of responsiveness only happens when you're within a certain territory, right? If you're within this distance, you're close enough, then from this point forward, it will shrink down in scale as you get closer to it. And if you walk back away from it, out of this, then it's stuck here and it stops processing and it's back to its original scale. Okay, so this area of effect number is what I'm using to be able to set how big that area is. I'm going to show you two different ways to do this. One way to do it with math and one way to do it with geometry. One way to do it with algebra and one way to do it with geometry. So when I look at one of these cubes, and these are all instances of the same class, they all have the same behavior on it, you'll see that we expose all those public variables. So the object to track is the first-person controller. Here are those flags, those Boolean values. So I can say, I'm going to show you three different effects. One that affects scale, one that affects rotation, and one that affects color. So we can decide on a per instance basis, do we want them to track all three of those things, or just one or two of those things? Here's the area of effect, it's set to 5, and eventually we'll come back to this rotational velocity. So in the script, there's one concept that is a useful one to know. It's one that I would say is about good form more than it is about essential functionality, but it's just something good to think about. You've heard me say this before. In the computer, division is a really processor-intensive operation, right? It's like 16 times more intensive than adding. And our world of trigonometry is full of division, so we use linear algebra to avoid division. And even within that, one of the things that's really common and what we're doing here when we measure to see if we're inside of that scale is we're measuring the magnitude of that distance. Now the thing I want you to think about is if we, like, how do you calculate the magnitude? We calculate the length of a line using trig. Right? What's the equation? Right, like x squared plus y squared, take the square root of it, you get the and then the square root of it, right? So here's the thing. If instead of taking the square root to calculate the magnitude, if we leave the magnitude squared, and instead, if that's what we're comparing, we want to compare the length. So if I were to say, this is a distance of 5, that's what's set in my code right now, right? It says that if you're within 5 meters of this point, then this script will start to operate, okay? So we measure the magnitude of this vector. We find out, I'm right here, the magnitude of that vector is 3, let's say. 3 is less than 5, so we know that I'm closer to the object than this area of effect. Well, if I want to avoid division, what I can do is I can square this area of effect. So I take area of effect times the area of effect, right? Which is now what? It's now 25. So if I take the square of the magnitude and not the full magnitude, and I do that comparison, square of the magnitude compared to the square of my area of effect, I can do this comparison without performing a square root operation, which has all the heavy division that we're trying to avoid. Right? Does this make sense, conceptually, at least? The way this plays out in the code, I have the public variable, right? So I'm exposing to the user, or I'm exposing to the person who's making the game, or the simulation, what are my parameters? What can I change about this script, or this behavior? And that shows up right here, right? So area of effect is 5. But behind the scenes, I don't need the user to know that I'm doing all of this square root stuff. If you were in a video game studio, the analogy would be more, I don't need the artist to worry about the square root. The programmer does all of that on the back end, and then exposes to the artist, you only need to worry about 5, right? It's about abstracting away all of the sort of technical stuff that's happening and creating a black box. So the black box, though, inside of it, what we're doing is when we first start up, one of the first things I do, and I apologize, this projector is horrid. One of the first things I do is I take the area of effect S, area of effect squared, and I take the area of effect times the area of effect. So right out of the gate, as soon as I make that object, I quickly store the squared area of effect. And when I do my comparison further on down here, right here, it says if the delta vector, right, I made a vector from where is the player and where is the center of the object. So the delta vector is that vector. I take the square magnitude, which is one of the functions that's part of the vector class or the vector library in Unity, right? And I do that comparison. So if the square of the magnitude is less than the square of the area of effect, then I know I'm inside of that and I've done it without performing any division, okay? So just to clarify, there's an extra couple steps in here that technically we could have done all of this without doing that, but this will run 16 times faster or 8 times faster than it would have normally, okay? And that's maybe not a big deal when you only have 128 objects, but if you think about you're in a simulation, I know some of you have already started talking about animating people and people walking around and wandering in the scene. And if you think about a contemporary simulation, you might have thousands, tens of thousands, hundreds of thousands of objects that are all doing division at the same time, right? Or more or less at the same time. So when you start to get into that, you want to scale up. These kinds of things actually really matter, right? Now, in this script, so let's just walk through this. In the start, the first thing it does is it records its original scale. It says, make this variable, which is another private variable, it's a vector free called original scale, and store this.transform.local scale. So when I make this object, when it starts up and I hit play, the first thing it does is it remembers how big it was, right? And this is relevant because I could change, even though I have the same script, right? So there are 128 cubes in this array. Let me where here, right? So there's 128 cubes here, and right now they all have a scale of 1, 1, 1. But I could scale them each independently and still have the same script on it. So you can't hard code the starting scale because the starting scale theoretically could be different. Therefore, one of the first things we do in the script is we say, okay, I know that each one of you could theoretically be different, so I'm going to find out exactly what you are when we start up, and I'm going to remember it. I'm going to store it in the scale. And then I'm going to take that magnitude squared, or the area of effect squared, and the last thing I'm going to do is I'm going to make a reference. I'm going to get a component, and remember the components are all the different parts that are in the inspector on the right-hand side, and I'm going to get the mesh renderer component, and from this point forward in the script, I'm going to call it MR. And that's just so when I use it to change the color later, I don't have to type out get component, mesh renderer, etc., etc. I can just type MR. Right now, in the heart of the script, in the update, the first thing I do is I check to see, is this object that I want to track null? Is it empty? And it could be empty if you don't set it explicitly. It gets set in the editor, right? So that's right here. And I set this by grabbing my first-person controller in the hierarchy and dragging it to here. Or you can press the little target on the side and you can go to the scene and you can pick the thing that you want to track. All right? So in my script, it says, if the object to track is not equal to null, then we're going to think about doing some other things. But if it's null, if I'm not tracking anything, then it's done. It drops out, and the script does absolutely nothing. Okay? If there is something, then we calculate that delta vector. So we say the delta vector is equal to the position, this.transform.position, and this is the object, right? So the transform position of the object minus the transform position of the object to track, right? So now that creates a delta vector. Remember that the vector is magnitude and orientation, not position. Then I do that check. I say if the square of the magnitude is less than the area of effect, so now I know for sure that I have something to track, and I know that the thing that I want to track is within the area that I want to track it within, okay? Then I can start to do stuff. So now I have three if statements. If this dot rotate on, and if this dot scale on, if this dot color on, this corresponds to these three Boolean values. You should remember from last term that Boolean is ones and zeros, on and off, or in the case of most programming languages, true or false. Okay, so I've got, by default, they all set to true, but in my editor, I changed that. In my editor, right now, I have only scale on checked. So in the responsiveness that you saw when the character gets close, the box is scale, but they're not rotating and they're not changing color. That's because I have them, for all of them, turned off. Okay, now, let's look at the scale first. So if scale is on, if this is set to true, then we will do all the stuff that's in here. And if it's set to false, we won't do any of it. We'll just move to the next comparison, the next condition. If the color, if this is set to true, then it will perform this operation, right? Now, the scale here, you can see, we're going to set a scale factor. Once I know that this character is inside of here, I need to calculate some scale, proportional scale, based on the distance. And it's pretty easy. I just take, again, the square magnitude, because I don't need to use magnitude and have to do a bunch of division. I can avoid the square root. And then I take divided by the area of effect. So I'm creating a proportion. I know that the area of effect is 5. And I know that when I hit that point on the edge, my vector is going to be 5, magnitude of 5, right? So when I'm on that edge, this object will be scaled with 100%. And if I'm halfway, I'm at 2.5 magnitude, 2.5 over 5 is half. So now it's going to set my scale factor to half. But it's a question of half of what? Half of that original size, which is why I need to remember it. So the next thing I do is I say, set the local scale of this object equal to the original scale times the scale. Okay, now this is the thing that I had in our lecture last week. You remember this one. A vector multiplied by a single number or a scalar performs a scale of the vector, right? It changes the magnitude. So if I take this and I multiply it by 5, I'm taking each component, ax times 5, ay times 5, and I get a new vector that is 5 times the size. Of course, if I were to multiply it by 0.5, then that's going to shrink that vector. It's going to keep the same magnitude, the same direction. Sorry, not the same magnitude. It's going to keep the same direction. And it's going to reduce the magnitude by half. So it's really simple. Right? It just figures out how much should I scale an object based on how far away another object is to it. And I could use anything. I could use the player character, I could use a box, I could use anything that has a transform. And you should remember, because I've said it a million times, everything that's a game object has a transform. So it could be a light, it could be a camera, it could be a plane, a tree, it could be any of those things. Okay? So that's the scale. That's what you see working here. Change this. And then remember, when we're in runtime, when we're in the game, we can change these values on the fly. And they will all adjust. Because now I can be further away when the thing starts. So there's scale. Now, let's turn this off. All the cues selected. Let's set color on and rotate on. Now, okay, so now, not only do I get the reduction in scale, but I also get a reduction in the value, right? So I'm going from gray to black. And that's being done in the next script, the next section of the script below, part of the renderer. And so here, I make a reference to that MR. So I say, go to that object's mesh renderer, get its material, and set its color equal to the new color. And a color is a vector, right? A color is, for all intents and purposes, analogous. It's even usable, right? I could take a color and I could use it to move something in the space, because all it is X, Y, and Z, or R, G, and B, or in the case of an alpha channel, R, G, B, and A, right? So it's either a 3 or a 4 component vector that stores the different components of the color. And I'm using this concept of scale, and you'll see this again in a minute, in order to adjust. So, you know, color is, if we take and map R, G, and B along the 3 Cartesian axes, right? I know that if I'm somewhere up here in space, I have some value of R, G, and B. So everything that I can do spatially with vectors, transform, rotate, and scale, I can also perform within the 3-dimensional color model of color. So I can numerically change color procedurally, just like expanding and contracting the space. And I'm doing a kind of similar thing that I did before, right? So I'm taking the current local scale of the object, how big am I right now, and I'm dividing it by the original scale. So I go from, again, 1 down to half, down to something very small. And that effect is like reducing the volume or turning the dimmer down, right? I make the color go from high value with lots of white down to low value with more black. And so the objects that I'm closer to have been scaled down more and they're darker, right? Pretty straightforward. So this is what we covered in the morning yesterday, a little bit more slowly, but let's expand on it. So now I want to add rotate. And I want to illustrate a couple things that we talked about the other day. And that's in the lecture notes. So let's first try this. So if I say I have this rotational velocity vector. Now, there are a lot of ways to think about moving objects in the world in one of these simulations. The most customary is to either be velocity-based or acceleration-based. And what that means is that every object that is potentially a movable object in the world, usually in a game, in contemporary games, is storing what's its current velocity. Or, if it's a more sophisticated model, what's its current acceleration. So, a velocity vector, let's say a velocity vector of 0, 5, 0, right? If we apply that velocity vector, and the cool thing about vectors, this is a big part of the reason why we use it, if I have this object that's here, let's say this object is at 10, 10, 10, and once a playback cycle, I apply velocity, a constant velocity in this case, I can do it by saying, take this vector and add it to this vector. It's just addition. I just add velocity. So then this frame, it's at 10, 10, and if I were to add this vector to this vector, you remember you take the x component plus the x component, the y component plus the y component, and now we have 10, 15, 10. And if I applied that velocity on the second frame, then I would have 10, 20, 10, so on and so forth. And my object would start to rise in the y-axis, right? Now, if you're a little bit more sophisticated, you know a little bit about physics, you understand the equation, you could use acceleration calculated per frame to determine the velocity that gets applied. And instead of saying move this fast, you say apply these forces, right? And if you probably open up the code for the rigid body first-person controller, probably most of the movement is done through acceleration and the application of physics forces on momentum. So I'm going to use the velocity model. It's a little bit simpler to demonstrate this, but instead of it being, as you might customarily think, velocity is about translation or moving, right? 65 miles an hour down the road. I'm going to use rotational velocity. So my rotational velocity, unless I could do it with a vector, if I wanted to rotate about all three axes arbitrarily at the same time, I could use an XYZ vector. But instead, I'm going to have it just rotate around one particular axis that I define. And so this is just about degrees of rotation, right? So let's say if I have an object to track, and if the square of my magnitude is less than the square of my area, I know I'm inside of it, and I'm not using division, then I want to rotate. So now I could say this dot transform dot rotate rotates a function or a method, and you can see here when you get this little pop-up, this is like your best friend, because this is showing you the sort of protocol for what kind of input needs to go into these parentheses, right? It's asking for a vector 3, and that vector 3 is the Euler angles, right? So that's the amount of rotation in radians around the x, y, and z axes, right? So I can rotate however I want in space. Now, also notice this says 1 of 6. That means there are 6 different ways that we can use parameters. There are 6 different parameter sort of patterns. So if I look, I can add my Euler angles. I could add an axis. Which axis do I want to rotate about? And I could define that as any axis in 3-dimensional space, and the angle. I have another one which is Euler angles, and then this sort of spatial relativity thing. Axis angle relativity, angle, 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 angle relativity. So there's all these different ways that I can do it. I'm going to use this second one, which is I'm going to define a vector which says this is the axis that I want to rotate about, and then the angle that I want to rotate. So what vector or what angle is this? How am I going to rotate if I do it this way?
Y-axis.
Like this, right?
Yeah.
Because the axis is a vector that is nothing in the 0x, 1 in the positive y, and nothing in the z, right? So it's saying rotate around this axis. So the object will rotate around that axis. It's in the update loop. So once a cycle, once a frame, it will apply whatever I set as my rotational velocity speed. In this case, I have it as a unit of 1, and it will rotate. So now let's see what happens. So as long as I'm in there, it's just going to keep rotating 1 degree. Now it could be, instead of rotating 1 degree, maybe I make the rotation proportional to my distance as well, so that ones that are further away rotate more or rotate less, right? Okay, let's do something a little bit different. Talked about this, we mentioned it, we talked about it a little bit in class yesterday. Back in the 80s and through the early 90s, when our computers were super weak and we knew we could do all this, right? The math hasn't changed. None of the math is any different. None of the goals are any different. The only thing that's different today than then is the processor power, right? So back then, when we had to really worry about processor power, something that was really common to do was in your simulation, you would make a plane infinitely thin. You would put your tree on it, right? And if you were in the scene and you were looking perfectly perpendicular to that tree, if you made this an alpha channel, right? You guys should know now about mapping and about opacity maps, right? So if you take a material like a tree and you have the brown and the green and the raster image, and then you add an opacity map to it so that the alpha channel has black all the way around the tree, then what we see when we render is we don't see any of this because that's all transparent. We see just the tree, right? And it looks good when we're straight on. But when we stand here, and we look from the side, we realize that that tree is infinitely thin. So one of the things that was really common to do in simulation in the late 80s and early 90s was called billboarding. So that this tree would rotate based on where the camera was at. So it was always trying to be perpendicular to the camera. So the trees were effectively rotating. It happened smoothly, so you wouldn't see that rotation or perceive that rotation. It just made it look like a three-dimensional tree. Right? With only, because this is all polygon based, with only 2 polygons. Now, make a tree in Unity, and that tree is probably 10,000 polygons if you're not careful, right? Because the computational power is there and we don't have to worry about it as much. But we could still do some pretty interesting things with that, and Unity knows that, so there's a function built in to the transform. So every object that has a transform has a method called lookAt, and all it takes is a vector. What vector, which is a positional vector, what position do we want to look at? So let's just say this dot object to track dot transform dot position. Now I've got 2 positions. I've got position and I've got local position. Got to be careful here, right? Because remember that this world is relative. So my local position is a child to a parent. So maybe it's only 0, but that child or that parent could be at 10,000 units in the world, and so you're not looking at the right vector. So if you use the position, this is the world vector. And it'll say that if you, the position of the transform in world space. So that's what we want. Let's comment this one out. particular area of effect, it has a forward direction vector. It's the z-axis. By default, the z-axis is considered forward direction, right? So it takes the z-axis of every one of those objects, and it finds the position, and it rotates the object to point at that point, right? And you can see it's not a two-dimensional or a rotation about a single axis, but it's a rotation about all three axes. Okay, so this is the example that's posted, less these rotations. So I've given you scale, and I've given you changing color, right? That's your starting point. Everybody should be able to do that. Everybody should be able to take that script, put it on an object, set up the scene, modify the variables, and if you do that minimally, which you should technically be able to do in about 10 minutes, you'll get a D for the assignment. Right? That's sort of my standard. If you're in my class, that's what you do. That's D caliber work, right? You've had to do next to nothing. If you want to do C work, you'll add a little bit. You add B work, you'll add a little more. You want an A, you'll add a little more, and you'll do it with Minecraft, right? So it doesn't take a lot to be able to make this work. Now, I'm going to show you another example here. Let's make a new cube. Make this one bigger. This first example was based on algebra, right? It was based on, I've got one position here, I've got another position here, I'm doing this comparison to see if I'm inside. Another way you can approach this is by the use of triggers. So every primitive, and if you make meshes and import them in, you're going to have colliders and renderers. We talked about this a little bit last time. If you have your collider on and your renderer off, it's like an invisible wall. You'll bump into it and not be able to go further, but you won't see what you're bumping into. And if you have your collider off and your renderer on, you'll be able to walk right through that object and not bump into it, but you'll be able to see it. Right? So if an object has a collider, it's, as the name implies, there's a collision detection system. In every tick of the playback, the collision detection system is finding out how many things have collided with each other. And if we want, we can then react to those collisions. So it might be about, in a game, it's like somebody pointed a gun and shot a bullet, and there's literally a representation, and you might not see it. It might only be computational representation, but there's a representation of that bullet. And that bullet is firing out, and physics is simulating the movement of that bullet. And then it checks to see, did it collide? So in a game, it's like, oh, did it collide? Did it collide with a head? Did it collide with a hand? Right? Because if it collides with the head, then the guy's probably dead. And if it collides with a hand, then the gun is probably going to get knocked out, right? Like, these are the things that are actually happening. It's not art. It's simulation. It's science that's interpreting this. Okay? Or it's an artistic use of science. So, triggers. If I check is triggered, this collider will now let me run into it and through it. And it will allow me to trigger an event that does something. But I have to set up my script a special way in order to do that. So I've got another script here, my trigger example. I'll throw this onto here. Set the color. Okay, so I'm inside of this thing now, right? Like, come back outside of it. I go inside of it. Starts changing. Come back out. It changes back. Okay.
Same thing, it's a mono behavior. I've got a public variable color called transition that I set initially to magenta. By making that public, that's what then, like the other times, exposes in the editor what do I want the transition color to be. And if I click on it, I can set it to something else. So that's that part of it. Like the other one, we make a reference to the renderer called RAND here. And just like before, in the start, I say render equals, and I get the component. So from that point forward, I just have to write this, and I don't have to write that. And then I set my material color equal to blue. It could be, if I wanted another way I could do this, would be to say, instead of using the preset colors, right? So there's the color class, and there are all kinds of preset colors as part of the color class. So I could use any of these that I wanted. The other thing I could do here is I could say I want it to be a new color, and you can see there are 3 different ways of entering color. So I can enter a red, a green, a blue, that is just as valid a way to set the color. Now I can be super specific about it. Nothing happens in the update, which is kind of peculiar because you saw once I'm inside of it, it still was doing a kind of slow transition of color. It was still doing stuff during the update cycle, but not because of the code that was in here. These 3 pieces of code, often referred to as delegates, are specific reserved functions, kind of like start, kind of like update, on trigger enter, on trigger stay, on trigger exit. So these are reserved. If your object is a trigger, you have a triggerable collider, then when these things happen, when you enter into the trigger, it will do this stuff. And when you stay in the trigger, it will do this stuff. And when you leave the trigger, it will do this stuff. Okay? So the first thing it does is it says if other.name is equal to first person controller. Now this is something new. And this is tied, if you look closely here, this first line, the function says on trigger enter, and the parameters of that function, the things that get passed into it, are an object called other that's of type collider. So the first person controller also has a collider. So what happens is every time an object collides with a triggerable collider, it will get past that object. And if 20 things go into that, then 20 things will get processed, okay? But we might not want to process everything that runs into it, right? We might not want to process the bullet. We might want to let the bullet pass right through. But we might want the player to do it. So here I can do a check, and I say if other, which is the thing that was passed in, because every object in the world has a name, I can say if other.name is equal, remember equal is a test of equality, a full test of equality. If other.name equals FPS controller, then I want to do something. And if it doesn't say that, then it's not the thing that I'm worrying about, right? So this is the way that this script is handling what things should be tracked, okay? It's done through name, not by explicit definition as a game object. And if that's the case, if the thing that bumped into the trigger is called an FPS controller, then set its color equal to whatever that transition color is. That's on the enter. So the first time I walk into that trigger, it's going to instantly set it to another color. No fade, no transition. And then, if I walk out of that color, it automatically sets it back to another color. In this case, it sets it back to blue. Maybe we would want to have original color and transition color. But when I'm inside of the trigger, when it's in stay, I'm inside of it, I can move around in it. But if I'm inside of that trigger, it's going to do something else. It's going to say, set the transition color equal to color.lurk. Okay, so lurk. Lurk is an acronym that stands for linear interpolation. Lurk is linear interpolation. And all that's saying is that if I have some reference here and some reference here, and I want to go some percentage of the distance from here to here, I don't know where these vectors are at. They're vectors in three-dimensional space. The LERP equation will let me say start, end, and I don't know, 50%, and we'll find the place that is 50% in between those vectors, or 10% inside of those vectors. So what this line is doing, again, we're not LERPing in space. We're not LERPing in XYZ Cartesian space of the world. We're LERPing within the RGB color space of a color. First color is the transition color. Second color is yellow. And the third value is the percentage that I'm going to move in the direction from one color to another color. Okay? In this case, 0.01, so it's really small. So if you notice when I go inside of the trigger, it switches to that color that I set, and then it slowly, over time, starts to transition towards yellow. And it'll go, and eventually it'll get here to full yellow. And when I come back out of it, it instantly gets set back to the blue. Okay? Does it make sense? So one way to track is by measuring magnitude, having some sort of distance, and seeing if I'm inside of that. Another way to track is by making a trigger. Now, if you combine these two, right, because this example, the thing that's being modified by the code in the trigger is the object that is the trigger, right? I think most commonly you're going to want to combine the two. You're going to want to have a trigger that knows about another object or objects, and if I go inside of that trigger, it will tell those other objects what to do. And that's the example that's set up in the first one, right? An object to track. So, again, if you want to get a better grade on this assignment, you'll think about how you might combine these two scripts together that aren't already combined together. Okay? This is here, so I just put this back in so that you would have reference to these things. All right, Unity build settings. From this point forward, when you submit your work, when you bring your work on Tuesdays, or sorry, on Thursdays, when you submit your work into our Google Drive folders, you need to export a full build, okay? Because projects and assets and all this stuff, they're bigger, they're more unruly, there's just kind of more unnecessary stuff to deal with. So let's just walk through this process. Professor Putnam put up some slides, a link to this manual here. You can check this stuff out, but let's just walk through what we're talking about. Look here at build settings first. Okay. So right now, there's no scenes in my build. I need to add my scene. And maybe towards the end of the semester, you guys will get to a point where you have multiple scenes and you start switching between scenes. But right now we have one. So what I'm going to do is I'm going to add my current scene. And now I've got my target. These are my platforms. Which platform do I want to publish to? This is a big part of the reason why Unity has the market share that it has, why Unity is as powerful as it is, because with this one code base, I can deploy to the web, I can deploy to a PC, Mac or Linux as an executable, iOS, Android, Windows, BlackBerry, Xbox, PS3, whatever you make is now publishable to all of those platforms more or less at the click of a button. That's what's really significant about Unity. So if you want to be an iPhone game developer, This is hands down the easiest and most direct way to make games for an iPhone. Now, you could also make other apps with this for the iPhone, but it's really obviously optimized towards games. Now, you do have to have the right license in order to be able to use those, but you should know it. So, you're going to want to do this one, PC, Mac, and Linux standalone. And then, of course, you need to pick your target platform. We would like for you to pick, you don't have to do it for yourself, obviously, Windows. If you have a Macintosh computer, you can publish to Mac and run them locally, that's fine. But when you submit your homework, you should submit using Windows, okay? And then platform x86, that's fine. Development build, by checking development build, it gives us a little bit more sort of access to troubleshoot when things are not working right. This isn't requisite, but it's fine. And then the other thing you can look at here, if you look at the player settings, this won't be such an issue now. All the defaults will be fine. But when we move into the final phase, when we start to connect the Arduinos to Unity, we're going to have to make sure that we're not using the .NET 2.0 subset, but that we're using the full .NET 2.0 library. Okay. Now I say build, and it then generates all of this stuff. So the PDB we don't really need, but you need that executable file, DC4 week 3, and you need that folder DC3 week 3 data, right? So if you copy all of those things, and my recommendation is you just make, every time you make a build, make a new folder for that build. And then what you know is you need everything that's inside of that folder. If you don't give us that data folder, then we can't run your simulation. Okay? But this creates an executable file that now you don't need Unity to be able to run. So if you want to send this file to your parents and have them be able to click on it and run it on their computer, they can do that. Okay? It's a fully legit executable file for whatever platform it's being deployed to. Right? This is how you should come on Thursdays, and this is how you should submit your work on the Google Drive folders from this point forward. Okay? This will make Thursday's work a lot better. Trigger events, we'll put together some stuff about that too, some more links. And then Xbox controller input. So I've already fixed this on this, but I'll show you where we do it at. If, I don't know, some point along the way, Unity changed their first-person controller and the way it's configured and mapped to the controller input. So chances are, if you plug a controller in, maybe even with your mouse, it depends on how it's set up, you will be able to move in the world, but not look around in the world with your right stick. And to change that, we need to go into the input settings. So we do that by here, edit, project settings, and input. Okay, so this is the input manager. You'll see we have a bunch of different inputs. The ones that we're really thinking about now, if you want to control where the player is looking, you want to adjust the mouse X and the mouse Y axes. And you want to switch this from mouse movement to joystick axis, and the axis from Y-axis to fourth axis. And for the mouse Y, change that from mouse movement to joystick axis.
axis to fifth axis. Now the other thing that I did is adjust the sensitivity. It was pretty slow at first, so I increased that to make it a little bit more responsive. Next week, we're going to go into more depth about how to look at input, how to measure input. Is somebody pressing a button or not pressing a button? Are they pushing the stick? Are they pushing it halfway? Are they pushing it all the way, right? So to be able to get the information, the input information that the user is trying to give you, how to process that. That will be the next step of the assignment. And we'll also look next week at creating user interface elements. So if you want to have a button or a slider or some kind of thing that's like a typical GUI interface, how do you interact with that? How do you use the script to respond to it in some way? And so we'll come back to this input settings next week. And I'm done. So, any questions?